Hi everyone, welcome back. In this video, we're going to be talking about partial derivatives. So far you've done lots of derivatives when there's only one variable. In this section, we're going to be talking about how to take the derivative of a function that has more than one variable, like let's say x and y or x and y and z and so on. So as a rule of thumb, basically you're still using all the rules of derivatives that you know, so like product rule, chain rule, quotient rule, power rule, and so on. You're still using all of those, except with partial derivatives, they're going to specify to you which variable they want you to differentiate with respect to. So for notation purposes, they're going to give you something like f subscript x, just like I wrote there. And what this means is basically take the derivative, treating x as the variable, and treat y as a constant. So basically treat y in any other variable as a number, like 2 or 3 or something. Similarly, if you're given fy, you basically take the derivative, treating y as the variable, and you treat x and any other variable as a constant. So in order to understand this concept, we do need examples. So let's go right into it. Alrighty, so let's do an example. So for number 1, we've got this function here, and we're gonna actually take both partial derivatives, fx and fy, so that you can see the difference. So if I start with fx, basically I'm taking x as the variable. So just underline anything that has an x in it. That's going to be your variable, and the other thing is a constant. So for example, the y cubed, the y, this -6, the 3 and the 2 and so on, all of those are going to be basically constants. So think about the way you would take these derivatives with just one variable. If you've got a constant, so y cubed is a constant here, if you've got a constant attached to a function, you would basically leave the constant where it is and just take the derivative with respect to x. So what I'm going to do is, okay, the first term, the derivative of x squared is just 2x. Y cubed, we don't take the derivative of it because this is a constant when we're differentiating with respect to x. Okay, the same idea, -2 times, the 2 is a constant, so it stays. The x turns into a 1, that's the derivative of x. And then the y is a constant, so we leave it. We don't take it away or differentiate it. Okay, and then plus similarly 3, and then the derivative of x is 1, and then the -6 becomes a 0 because that one is a constant not attached to any function, so that becomes a 0. And then we're just gonna simplify this, and then we're done. So basically 2xy cubed minus 2y plus 3, and that's your partial with respect to x. So that wasn't too bad. Now let's do it with respect to y so that you can see the difference. So what I'm going to do is just put a little squiggly thing underneath the y, and basically that is my variable part. So anything attached to that is a constant, and it stays where it is when I differentiate it. So when I take the derivative, x squared is a constant, so that stays where it is. And then the y cubed becomes 3y squared. And then the minus 2x is a constant. It's attached to a function with y, so I leave it. And then the y becomes a 1. Now the other part, the 3x is not attached to a function that it's not attached to anything that has a y in it. So that becomes 0. Okay. And then the -6 also becomes 0 because that's a lone constant. So here, just be careful with these two zeros, especially the first one, because people might think that you have to take the derivative of it, but basically it does go away completely because there's nothing attached to it that has a y in it. Okay, so now simplifying, I get 3x squared y squared. I bring the 3 to the front, it just looks a little bit nicer. And then minus 2x, and that is your partial with respect to y. And there's with x and then with y, and that's it. All right, now let's do something that's a little bit more complicated. So I've got a function with e in it. I know a lot of people get scared with e, but that's okay. We're gonna change it before I take the derivative. Just like in one variable, I always change the square root into an exponent of 1/2. It's the same thing. It's just going to be a little bit easier to take the derivative of. Now, the reason why this is a lot more complicated than the previous question is because you've got the x and the y, they're sort of attached to each other, and they're within a function within another function. So you have to be careful. We are taking the chain rule just like in one variable. So think about it. For fx, pretend, I'm just going to write it here and then I'm going to erase it because I'm going to need the space. But imagine you had, let's say, x minus 4 to the 1/2. Just picture it like that. The y is a constant. So I'm going to imagine it like a 4. I'm not going to write the 4 as part of the solution, but I'm going to pretend that it's a number like that. And think about what you would do if you were in one variable. How would you take the derivative of that? All right, so since it's a chain rule, I take the derivative of the outside function first. So I'm going to do e to the whatever. The derivative of e to the anything is itself. So I rewrite it times the derivative of the exponent. Okay, the exponent itself is also a chain rule. So the exponent, when I take the derivative of that, remember the half comes down. The inside stays the same. I take 1 away from the exponent, so I'm doing 1/2 minus 1, which is minus 1/2. And then I'm going to multiply by the derivative of the inside. The inside is the x minus y squared. So if I take the derivative of that, just take it one step at a time. The derivative of x is 1. And the derivative of y squared, well, that's not attached to a function with respect to x. There's a minus in between. It's not a multiplication. So the y squared is like a lone constant. It's like a 4, let's say. If you take the derivative of 4, you get a 0. So I get that. And then it's just a matter of simplification. Sometimes the simplifying is a little bit hard too, so just be careful. The 1/2, I'm going to bring it all the way to the front. The e, I'm going to keep it, x minus y squared to the half. And then this concept here, this part here, x minus y squared and negative 1/2, what I'm going to do is I'm actually going to bring it to the bottom. So because it's a negative 1/2 and everything's being multiplied, I can bring it down and make it into a positive exponent. So basically a positive 1/2. This 1 minus 0, I'm just going to cross it out. It's a 1. Okay, and I would simplify this one more step. So this 1/2 at the front here should really be going to the bottom. So I'm going to keep the e where it is. You don't have to. You could keep the half in front of everything. It doesn't matter. But it's 1/2 times something is like dividing it by 2. So I'm going to bring the 2 down. And then the 1/2 changes into a square root. And I get x minus y squared. Now, why I bothered with a simplification is just because on the test you might get that. I'm not sure what sort of answer you'll get, so I'm just putting it that way for you. And that's fx. Now let's do fy, which is the partial derivative with respect to y. So now you're treating x like a number and y as a variable. So the derivative, the first part is not going to be too different. The derivative of the outside, so e to the anything, when I take the derivative, I'm just going to rewrite it basically, and then multiply by the derivative of the exponent. Well, the derivative of the exponent is a chain rule. So I bring the half down, keep the inside the same, take 1 away from the exponent. And then I'm going to multiply by the derivative of the inside. And again, the derivative of the inside, x is a lone constant. It's not being multiplied by a function of y. So the x becomes a 0. And I'm going to do minus, and then the derivative of y squared is 2y. Of course, this requires simplification just like before. So the 1/2 I can bring to the front. The e, I can just rewrite it. I'm not going to change that really. And then times, now this, the bracket x minus y squared, I'm going to bring that to the bottom. So let's do that right now. I get x minus y squared to the positive 1/2, that the exponent changes into a positive. And then the 0 minus 2y, that's just simply minus 2y. Okay, now let's simplify one more time. So the 1/2 at the front and the minus 2 in that last bracket, they multiply to a minus 1. So I'm just going to go here, put a minus 1 or just a minus. And then the y can come to the front as well. Okay? And then I have times e to the x minus y squared to the half. And then just like before, that 1/2 exponent in the denominator can turn into a root. And there is my fy, so the partial with respect to y. Okay, so now let's do another example. I'm trying to slowly build it up so that it's a little bit tougher as we progress. But do a lot of practice before you get to the tougher questions, of course. So in this question, we've got a ln, we've got an exponent, we've got here two functions that are being multiplied. So I'm trying to sort of integrate more and more derivative rules so that you can see them. If I start with fx, which is a partial with respect to x, okay, so I've got an x right there, the x squared. I've got an x right there as well. And so when I take the derivative, again, x is a variable, y is the constant. When I'm taking the derivative of ln, review your notes if you forgot, but you basically do, you take the inner function and you bring it to the bottom. And then at the top, you're going to put the derivative of the inside of the function. So the derivative of the inside function is going to be 10x plus 0. You don't have to write the 0, but I'm writing it in case anybody wants to see it. The 2y was a constant not attached to any function with respect to x, so it becomes a 0. And then plus, and now x is the only variable. The rest, everything that follows it is a constant. It's being multiplied. The x becomes a 1, and then the rest has to stay because it's being multiplied by a function of x. So then I'm going to just simplify that. So I get 10x over 5x squared plus 2y, and then plus 2y minus 3 all to the 7. I just want to backtrack a little bit and just remind you, for the derivative of ln, you're always putting the inner function, in this case 5x squared plus 2y, you're putting that at the bottom. And then the derivative of the inner function goes at the top. So if you have to just go back and review a little bit, by all means do that. But here is the partial with respect to x, and there it is. Okay, similarly on the same page, we're going to do fy, the partial with respect to y. So now the derivative of ln, again, the bottom is going to be the same because you're just taking the original inner function, so whatever's inside of the ln. And then at the top, you're doing the derivative of the inside. Well, the 5x squared is a constant, not being multiplied by anything with y, so that becomes a 0. And then the 2y, the derivative of that is 2. Okay, plus, and now in the second part, the x is a constant times the function with respect to y, so we're going to leave the x where it is. For the 2y minus 3 to the 7, this is a chain rule. So if you think about the way you would take the derivative in one variable, that's how you would do it as well. You would bring the 7 down, keep the 2y minus 3 the same, take 1 away from the exponent, and then multiply by the derivative of the inside function, which in this case is just a 2. Okay, now this does require a lot of simplification. So I'm going to do 2 over 5x squared plus 2y. There's not much there. Plus, okay, the x, the 7, and the 2, all of those can combine to 14x. It just looks nicer to be on the front. And then you've got the 2y minus 3 to the 6. And that's it. And there's a derivative, or the partial derivative, with respect to y. Now, I'd like to keep the same function. And I've written down the partial with respect to x. And now I'm going to ask a different question here. I'm going to say, what's the double partial derivative? So basically, what's fxx for this function? So fxx just means take the derivative with respect to x twice. It's exactly how you would intuitively think about it. So basically, we've taken fx already. We don't need to redo it. And now we're going to take it again with respect to x. Now, of course, the function is very different this time. Here we've got the first part, we've got a quotient rule. So I know it's a quotient rule because the top function has an x in it and the bottom function has an x in it. Keep this in mind for when we do fyy. You're going to see how it's different. Okay, so remember quotient rule, derivative of the top, which is 10, times the regular bottom function. So I'm just going to rewrite that, minus the top, so the regular top function, times the derivative of the bottom function and still with respect to x. So this would be 10x, and then the 2y becomes a 0 because again it's not being multiplied by derivative with respect, or sorry, it's not being multiplied by a function with respect to x. Okay, and then the bottom squared. So this is quotient rule the way you've learned it in the previous calculus courses. And then plus, now what do I do with the 2y minus 3 to the 7? Well, all of that doesn't have an x in it, so that becomes a 0. Okay, and now I'm just going to simplify. So this is just going to be, so the 10 is going to multiply into the bracket, and then these two terms are going to multiply as well. So I'm going to get 50x squared plus 20y minus 100x squared divided by, and then the bottom stays the same. I wouldn't expand it. I don't think they're going to expand on the test, so don't bother with that. And the x squared and the x squared, those can combine to minus 50x squared plus 20y, okay, because it's 50x squared minus 100x squared. And then again, dividing by the bottom that we're not going to change at all. And there it is. So that's fxx. Okay, now let's do f double y. So basically the second derivative with respect to y. I've written out the first derivative. We already did that. Now, in the first part, I've got two functions again, top and bottom. Only one of them has a y. Only the bottom has it. So you can still use the quotient rule. That's fine. It's just that you have to remember the top is a constant. So when I take the derivative of the top, it's going to become a 0. Okay, so the top, so derivative of the top times the regular bottom minus the top function regular without taking the derivative, and then times the derivative of the bottom with respect to y. Okay, the 5x squared doesn't have a y in it, so that becomes a 0, and then plus 2 for the y, and then we're going to divide by the bottom squared as we've already done. Okay, and then plus, now the second part, 14x is a constant, so we're going to keep that as is, and then we're going to multiply by, and now we're going to take the derivative of the second part with respect to y, so bring the exponent down. This is a chain rule, and 2y minus 3 to the 5, and then multiply by the derivative of the inside, which with respect to y, it's going to be a 2. The minus 3 will become a 0. Okay, so to simplify this, I would get 5. Oh, pardon me. Actually, the first part should become a 0, right? So basically, this becomes a 0. The second part is just going to become a minus 4, and then divided by 5x squared plus 2y all squared. The second part, you've got 14x, you've got a 6, you've got a 12, or sorry, you've got a 2. So if I multiply them out, I'm going to get 168. So I'm going to do plus 168x, and then 2y minus 3 to the 5 will stay the same. We're not able to bring the 168x into the bracket because it's got an exponent of 5, so we shouldn't be doing that. And basically, that's your second derivative with respect to y, and there it is. So compare that with the second derivative of x and see if you can follow along. Okay, so the only thing that I haven't covered is what if you have fxy? So basically, if you have that, it means you are taking two derivatives. Either you take the partial with respect to x first, and then you do it with y, or you can start with y and then do it with x. Now, the reason why I'm saying that is specifically for this course, these two, fxy and fyx, are actually the same. So it doesn't matter whether you start with x and then you do it with respect to y, or you start with y and then you do it with respect to x. Either way, they will be the same only for this course. So I'm putting that disclaimer just because it's not true in general, but for 1MO3, the functions that they will give you will allow you to do it in any order you want. Okay. Okay, so that was my lesson on partial derivatives. I hope it's helped you and I hope you can understand the concept better now. I cannot emphasize the importance of doing lots and lots of practice. The only way you're going to excel at the subject and at this concept is by doing lots of practice. So what I would recommend is to go back to the questions I've done in this video, see if you can redo them on your own. If you cannot, then just come back to the video and then follow along. Thank you so much for watching, and we'll see you next time.